Hello, my name is Sean Goodrich. I'm going to be doing my last video on the unit step function, or as it might also be referred to, the Heaviside function. Sorry about the spelling mistake there. It's named the Heaviside function because of the person who found it. Um, it's not a huge topic. We cover it in 2 lecture videos during this section, but it's something that's sort of important because it's going over piecewise functions and graphs, which we've seen all the way from middle school till now. Um, it's either displayed like this or with an H, lowercase or uppercase. In the book and in the notes, you're going to see it displayed like this. In programs like MATLAB, Maple, or Mathematica, you might see it displayed as an H. If you're in engineering, the H is going to probably be more helpful for you than it would be uh, right now in this class. So if you think about it, the unit step function is pretty much just a Laplace transform for a piecewise graph, and you can get the inverse Laplace transform of a function going from s to t to give you a piecewise function. So if you're trying to graph something that's sort of scattered, you can do that. Um, it's defined by u of t equaling a piecewise graph or function 0 when t is less than 0, or at 1 where t is greater than or equal to 0. Um, the other thing to note about the Heaviside function is that it's cumulative. So when you're going through and looking at numbers in a piecewise function, so theoretically here, if we had a piecewise function that looked like this, where it goes from, let's say, 5 to 7 to negative 10, when we're writing out the Heaviside function, we want to make sure that we know that it's starting at 5, then you have to add 2, your Heaviside function, and then going to that negative 10, we're going to subtract 17, Heaviside function, blah, 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 whatever in there. So it starts at 5, goes to 7, subtract all the way to 10, negative 10. So you're making sure that you're cumulatively thinking of how you're going through this graph. So, where each segment of the graph is. Um, so I'm going to be going over 2 examples. They're sort of the inverse of each other from WebWork 14, problems 5 and 6. This is problem 5 right here. And then down below, we have problem 6. And they're pretty easy, but they're a good way to go over this topic because not only are we writing out what the Heaviside function would be or the unit step function, but we're also thinking about the Laplace transform. So just to think about the Laplace transform real quick, the Laplace transform of the Heaviside function would be, if it had one, whatever number is in front of it right here, e to the negative a t over, sorry, a s over s, and that, sorry, that's a plus right there. So it's e to the a s all over s. Just want to rewrite that so it's a little bit more clear. A s s. So the first function we have here is 0 if 0 is less than or equal to t and 5 is less than or equal to t. 2 if 5 is less than or equal to t, and then t if 7 is less than t, and then 0 if 7 is less than or equal to t, t is less than infinity. So thinking about the cumulative aspect of this, you always want to start with this first number. It's going to be 0 right here. We're just going to show it. You don't technically need it in this situation. And then we have to add 2 to get to the 2. And then we know that we're changing this function at h for the Heaviside function of t minus 5 because it's starting at 5. It's this number right here. And I'm using the heavy step function because, or the Heaviside function, because we're in web work and that's what it requested. It's probably a lot easier than finding the symbol for that weird U. But cumulatively as we go along, we know that we have to get back to 0. So we're going to subtract 2, put our Heaviside function in, and then we get t minus 7. So now what we can do in this situation is create the, or find the Laplace transform. So just because there's a common factor of 2, I'm going to bring the 2 out front, and we get the Laplace transform of h t minus 5. And if you notice, I'm going to separate these two like a complex Laplace transform to make it a lot easier to solve. And then it's minus the Laplace transform of the Heaviside function t minus 7. So that gives us 2 times e to the negative 5s over s minus e to the negative 7s over s. And that's the answer. And if we took the inverse Laplace transform of this, we could then negotiate trying to make this function, this piecewise function right here. Below we have problem 6, which I said is the opposite of problem 5 in what we're doing. What we're going to try and find here is the numbers that are going in for the piecewise function. We notice that there's nothing in front of this h, so we can assume that it's 0. So we're just going to add that in to sort of make it easier to understand what's going on here. So we have 0, and then we have a 1 in front of this h and a 1 in front of this h, and we know that it's cumulative. So we're going to put a 1 here, and we're going to add 1 to 1 to get 2. So this is the piecewise function of this Heaviside function that we've just looked at. So the last thing we need to do is find the Laplace transform of this Heaviside function. And we're just going to separate it individually again. So the Laplace transform of h t minus 3 plus the Laplace transform of h t minus 8. And that gives us e to the negative 3s s plus e to the negative 8s over s. So in this situation with these graphs, it's showing how the graph is moving. So I'm going to draw this one out real quick. So we're just going to go by intervals of 2. So 2, or 6, 2, 4, 6, 8. And we know that at 0, so right here, this function is moving from 0 to 3 at 0, and then it jumps up at 3 to go from 3 to 8 at 1, and then at 8 going all the way to infinity, it's at 2. Don't mind my circle points here. They are probably incorrect. So pretty much it's just allowing you an easy way to get the the Laplace transform or the inverse Laplace transform of a piecewise function to either get what the Laplace transform is in an easy equation, or to find out what the original piecewise function was from the easy Laplace transform equation that you find. Again, I know it's pretty simple. I hope it is a good refresher for some people. Um, there's also there's another function. I can't pronounce it at the moment, but it looks like that. Don't confuse the two. There is a different Laplace transform for that. So good luck on your test, and good luck on the final. Thank you.